Look up at the night sky on a clear evening, and you'll see countless stars glittering like distant beacons. Each one is a sun, potentially hosting worlds of its own. But here's the staggering truth: every single one of those points of light is so far away that reaching them seems like pure fantasy. The closest star to Earth, Alpha Centauri, sits 4.37 light-years from us. That means even traveling at the speed of light, a journey that would take over 4 years, with our current technology, it would take tens of thousands of years just to send a probe that distance. But what if we could change that? What if, within our lifetime, humanity could send a mission to another star? Imagine witnessing the first close-up images of an alien world orbiting another sun, knowing we made it happen within a single generation. This isn't science fiction anymore. It's the audacious goal of Project Starshot, a plan to launch tiny, laser-propelled spacecraft at 20% the speed of light, cutting the travel time to Alpha Centauri down to just 20 years. Think about that for a moment. 20 years. That's less time than it takes to pay off a mortgage or raise a child. A mission conceived today could reach another star before today's toddlers graduate college. The implications are mind-blowing. For the first time in history, interstellar travel isn't just a dream. It's a tangible engineering challenge with a real roadmap. But how? How could we possibly accelerate a spacecraft to such insane speeds? What kind of technology would it take, and what obstacles stand in our way? And perhaps the biggest question of all, what would we find when we get there? That's the journey we're about to take together. From the cutting-edge physics behind light sails and phased laser arrays to the mind-bending challenges of navigating between stars, we'll explore every facet of this monumental endeavor. We'll meet the visionaries pushing the boundaries of what's possible and uncover the breakthroughs that could make interstellar travel a reality within our lifetimes. This isn't just about reaching another star. It's about proving that humanity can think beyond the limits of our solar system and take our first real steps into the cosmic ocean. So buckle up. By the end of this video, you won't just understand Project Starshot, you'll feel the weight of its ambition, the scale of its challenges, and the sheer thrill of what it means to reach for the stars. Breaking away from traditional space exploration's slow, fuel-reliant methods, Project Starshot emerged in 2016 as a radical reimagining of interstellar travel. Spearheaded by billionaire tech investor Yuri Milner and the legendary physicist Stephen Hawking through breakthrough initiatives, this audacious project wasn't born from a government space agency or aerospace giant, but from private ambition and scientific urgency. Their vision was clear: if humanity waits for conventional rocket technology to bridge the cosmic void, we might never reach the stars. So they proposed something revolutionary: a fleet of gram-scale nanocrafts, no heavier than a paperclip, propelled not by rockets but by giant Earth-based lasers. The inspiration traces back to ideas that once lived only in labs and science fiction. Light sails, ultra-thin mirrors that catch momentum from photons like a kite riding the wind, had been theorized for decades. But Project Starshot was the first to treat this not as a far-off concept but as an engineering blueprint. Imagine stacking the power of millions of lasers into a single coordinated beam, firing at a sail thinner than a human hair. That concentrated push could accelerate these tiny probes to 1/5 the speed of light, fast enough to slash the journey to Alpha Centauri from millennia to mere decades. What makes this project extraordinary isn't just the technology but the timeline. While Mars missions or lunar bases unfold over generations, Starshot insists on urgency. Its founders didn't want this to be a legacy for future civilizations. They aimed for results within the lifetimes of people alive today. That's why the team includes some of the brightest minds in physics, materials science, and aerospace engineering, all racing against an almost poetic deadline, proving that humanity can touch another star before Hawking's generation passes the torch. Yet ambition, this grand, faces staggering hurdles. How do you design a camera, computer, and power source small enough to fit on a postage stamp but rugged enough to survive 20 years in interstellar space? How do you keep a laser beam precise enough over millions of miles to avoid missing its target? And perhaps most haunting, how do you ensure these probes, once they arrive, can actually send data back across the unimaginable distance to Earth? Each question is a mountain to climb, but that's what makes Starshot so electrifying. It's not just a mission, it's a manifesto, proof that when science refuses to accept impossible, even the stars aren't out of reach. Behind every world-changing idea, there are minds bold enough to believe it's possible. Project Starshot is no exception. Its driving force comes from an unlikely alliance of visionaries, each bringing a unique perspective to the table. Take Yuri Milner, the Russian-Israeli billionaire who made his fortune in tech investments but whose true passion lies in the stars. Unlike traditional philanthropists funding incremental science, Milner wanted a legacy written in the cosmos. His breakthrough initiatives, launched in 2015, weren't just about writing checks, they were about accelerating humanity's reach into the universe. But even a billionaire's ambition needed a scientific compass, and that's where Stephen Hawking came in. Hawking's involvement wasn't just symbolic. The late physicist, who spent his life unraveling the mysteries of black holes and time, saw Starshot as more than an engineering feat, it was a survival strategy. In his final years, Hawking became increasingly vocal about humanity's need to become a multi-planetary and eventually interstellar species. His stark warnings about climate change, asteroid impacts, and other existential threats gave Starshot an urgency beyond curiosity. To Hawking, these tiny probes weren't just scientific instruments. They were the first lifelines cast into the cosmic ocean, ensuring that even if Earth faltered, human ingenuity would endure among the stars. But turning philosophy into reality required more than big ideas, it needed breakthrough engineering. That's where minds like Dr. Avi Loeb entered the picture. The Harvard astrophysicist, known for his controversial work on interstellar objects like Oumuamua, brought a pragmatic edge to the project. Loeb's research on light sails and laser propulsion became foundational to Starshot's technical plans, proving that the science wasn't just speculative, it was grounded in equations waiting to be tested. Meanwhile, Pete Worden, former director of NASA Ames Research Center, lent his decades of aerospace expertise to navigate the bureaucratic and logistical hurdles of such an audacious mission. What's fascinating about this team is how their motivations intertwine like threads in a larger tapestry. For Milner, it's about inspiring the next generation to think cosmically. For Hawking, it was a hedge against extinction. For Loeb and Worden, it's the pure scientific thrill of pushing boundaries. Together, they embody the dual nature of Starshot: part optimism, part necessity. And let's not forget the unsung heroes, the engineers and material scientists tackling problems like building a sail that won't vaporize under a gigawatt laser, or designing a microchip that can survive decades of cosmic radiation. Their work proves that interstellar travel isn't just for dreamers. It's for problem solvers who see obstacles as invitations to innovate. That's the real magic of Starshot's coalition. It's not just about having resources or brilliance. It's about aligning those forces toward a single, staggering goal. When history looks back on this project, it won't just see a mission, it'll see a moment when humanity's greatest minds decided the stars weren't just points of light but destinations. Alpha Centauri isn't just another twinkle in the night sky, it's our cosmic next-door neighbor, a triple star system hanging a mere 4.37 light-years away. That might still sound impossibly distant, but in astronomical terms, it's practically a stone's throw. Picture Earth's neighborhood as a vast city. If our sun is one house on a quiet street, Alpha Centauri is the house right across the road, close enough to wave at. This proximity makes it the obvious first target for humanity's interstellar ambitions. But what exactly are we aiming for? At the heart of the system, there's Alpha Centauri A and B, two sun-like stars locked in a graceful dance around each other, orbiting so close they'd fit within the distance between Saturn and our Sun. Centauri A is a near twin of our own star, shining just a bit brighter, while Centauri B is slightly smaller and cooler, glowing with a more golden hue. Together, they're the VIPs of the system, but the real showstopper is their quieter sibling, Proxima Centauri, a dim red dwarf lurking farther out. Despite being the smallest and faintest of the trio, Proxima holds a game-changing secret. It's the closest star to Earth in the entire system, and it might host a world that could change everything we know about life beyond our solar system. That world is Proxima b, an exoplanet discovered in 2016, nestled snugly in Proxima's habitable zone, the region where temperatures could allow liquid water to exist. Scientists call it a super-Earth, slightly more massive than our own planet, with a year that lasts just 11 days. But here's the twist: Proxima Centauri is a feisty star, prone to violent flares that bathe its planets in radiation. Could life survive there? It's a tantalizing question. If extremophiles on Earth can thrive in volcanic vents or frozen tundras, who's to say Proxima b's hypothetical organisms haven't adapted in extraordinary ways? Beyond Proxima, there's another reason Alpha Centauri A and B fascinate astronomers. While no confirmed planets orbit these twin stars yet, their sun-like properties make them prime real estate for Earth-like worlds. Imagine a planet circling Centauri A, basking in light almost identical to ours, or one orbiting Centauri B, where sunsets might paint the sky in deeper golds. The James Webb Space Telescope and future observatories are scouring the system for hints of these undiscovered worlds, and if they exist, they'd be irresistible targets for Starshot's tiny probes. But why focus on Alpha Centauri when there are billions of stars out there? Simple, time and energy. Even with Starshot's proposed 20% light speed, sending a probe to the next closest system, Barnard's star, would add decades to the mission. Alpha Centauri isn't just the obvious choice, it's the only one that makes sense for a generation-spanning project. Every gram of weight, every joule of energy, and every second of travel time matters when you're racing against the limits of human lifespans. So while the stars beyond Alpha Centauri whisper their siren songs, this triple-star system stands as humanity's first stepping stone into the interstellar dark. Whether it's the potential of Proxima b, the mysteries of A and B, or the sheer audacity of reaching another sun within our lifetimes, Alpha Centauri represents more than a destination, it's a promise. Proof that the universe isn't just something we gaze at, but something we might one day touch. And if Starshot succeeds, the light from those stars won't just be distant pinpricks anymore, they'll be places we know. The sheer scale of interstellar space defies human intuition. Crossing the gulf between stars isn't just a longer version of flying to Mars, it's a leap so vast that our ordinary ideas about travel collapse. Take chemical rockets, the workhorses of modern space exploration. Even the most advanced among them, like the engines that powered the Apollo missions, rely on burning fuel to generate thrust. But here's the catch: to reach another star, you'd need so much propellant that the rocket would become impossibly heavy before it even left the solar system. Imagine trying to bike across a continent with a backpack full of snacks, except halfway there, you realize you need another backpack just to carry more snacks for the rest of the trip. That's the tyranny of the rocket equation, a brutal law of physics that makes conventional spaceflight hopeless for crossing light years. This is why Project Starshot's laser-propelled nanocraft represents such a radical departure. Instead of dragging fuel along for the ride, these probes would harness the momentum of light itself. A ground-based laser array, kilometers wide, would fire a concentrated beam at ultra-thin sails attached to each probe. Photons have no mass, but they carry energy, and over time, that gentle push could accelerate the tiny crafts to relativistic speeds. Think of it like a cosmic game of ping pong, where trillions of photons bounce off the sail, each adding a minuscule nudge that collectively adds up to velocities once reserved for science fiction. But this elegant solution comes with its own set of nightmares. First, there's the problem of precision. To hit a sail no wider than a dinner plate from Earth's surface, the laser beam must stay perfectly focused over millions of miles, like threading a needle while standing on a spinning carousel. Even the slightest atmospheric distortion or mechanical tremor could scatter the beam, wasting precious energy or missing the target entirely. Then there's the sail material itself. It needs to be lighter than a sheet of paper, stronger than diamond, and reflective enough to avoid absorbing lethal amounts of heat. Scientists are experimenting with atom-thin nanomaterials like graphene, but one miscalculation could turn the sail into a puff of plasma under the laser's fury. And what happens when these probes finally reach their destination? Imagine a spacecraft the size of a postage stamp screaming past Alpha Centauri at 43,000 miles per second, too fast to brake or orbit. It might have mere minutes to snap photos, collect data, and transmit everything back to Earth across the mind-boggling void. The signal, weaker than a whisper by the time it reaches us, would require unprecedented advances in receiver technology just to decode. Every step of this journey is a high-wire act, with failure lurking in 100 unseen places. Yet the audacity of these challenges is exactly what makes Starshot so thrilling. Traditional rocketry is like trying to swim the Pacific with lead weights tied to your ankles, possible in theory, but doomed by inefficiency. Starshot's approach is more like catching a hurricane in a sail, dangerous, unpredictable, but harnessing forces beyond our control. It's a reminder that the universe doesn't owe us easy answers. If we want to touch the stars, we'll have to outthink the very physics that hold us back. And if we succeed, the payoff wouldn't just be a handful of data from another star. It would be proof that humanity can rewrite the rules of exploration itself. Light sails sound like something ripped straight from a sci-fi novel, vast, shimmering mirrors catching starlight to glide between the stars. But this elegant concept is rooted in hard physics, and it's the key to Project Starshot's radical approach. Unlike traditional spacecraft burdened by heavy fuel tanks, these sails rely on an endless cosmic resource, photons. Every bit of light, whether from the sun or a human-made laser, carries a tiny punch of momentum. Stream trillions of photons against an ultra-thin reflective surface, and that gentle pressure adds up to real acceleration. It's like holding your hand out of a moving car window. The rush of air pushes back, but if you replaced your palm with a giant sail, that same force could theoretically propel you forward. The genius lies in simplicity. A light sail spacecraft doesn't need to lug around fuel or engines because its propulsion system stays fixed on Earth, the laser array. This shifts the burden from the probe itself to ground-based infrastructure, allowing the craft to be absurdly lightweight. Picture a structure thinner than a soap bubble, lighter than a butterfly's wing, yet strong enough to withstand the concentrated blast of a gigawatt laser beam. Scientists are experimenting with materials like graphene or metallic foils just atoms thick, engineered to reflect as much light as possible while dissipating the insane heat generated during acceleration. But how does this translate to speed? Here's where the numbers get dizzying. A conventional rocket might take months to reach Mars, but a laser-pushed light sail could hit 20% the speed of light in mere minutes. That's over 100 million miles per hour, so fast that a trip to Pluto would take less than a week instead of a decade. The secret is the laser's relentless push. Unlike sunlight, which weakens with distance, an Earth-based beam stays tightly focused for thousands of miles, delivering continuous acceleration long after chemical rockets would have sputtered out. Of course, nothing this ambitious comes without hurdles. The sail must be nearly perfect. Any wrinkles, tears, or microscopic flaws could cause uneven thrust or catastrophic failure under the laser's intensity. Then there's the challenge of steering. Once the probes are en route, there's no way to adjust their trajectory unless we build even more lasers along the way. It's like firing a bullet and hoping it threads a keyhole halfway across a continent. Yet the potential is too staggering to ignore. Light sails don't just offer a shortcut to the stars. They hint at a future where humanity harnesses the fundamental forces of the universe to explore. Imagine fleets of these tiny crafts, each a silent ambassador sailing on beams of light, proving that the cosmos isn't a barrier but an invitation. And if Starshot succeeds, those glimmering sails might become the defining symbol of our interstellar age, not unlike the billowing canvas that once carried explorers across uncharted oceans here on Earth. 100 gigawatts is an almost unimaginable amount of power, equivalent to the output of 100 nuclear reactors channeled into a single, coherent beam of light. That's the staggering scale of the laser array Project Starshot envisions for propelling its nanocrafts, a ground-based installation so powerful it could theoretically push a postage stamp-sized sail to relativistic speeds in minutes. But generating that much energy is just the first hurdle. The real challenge lies in focusing it with inhuman precision across distances where even a microscopic deviation could send the beam veiling off into empty space. Traditional lasers scatter over distance like a flashlight beam fading in fog, but Starshot's solution borrows from cutting-edge astronomy techniques. By using a phased array, thousands of individual laser emitters working in perfect synchrony, the system can dynamically adjust its focus, compensating for atmospheric distortion and maintaining a tight beam over millions of miles. Think of it like the world's most advanced spotlight, one where every photon marches in lockstep toward a target no wider than a picnic blanket but from thousands of miles away. The engineering demands here are mind-bending. Each emitter must be precisely timed down to femtosecond, a fraction of a trillionth of a second, to prevent destructive interference that would weaken the collective beam. The array itself would sprawl across square kilometers, likely built in high-altitude deserts where dry, stable air minimizes scattering. And because Earth's rotation would constantly shift the laser's aim, the system would need real-time adaptive optics, correcting for turbulence faster than the blink of an eye. But perhaps the most counterintuitive aspect is how this gargantuan Earth-bound installation enables spacecraft to travel light. By keeping the power source on the ground, the probes shed the weight of fuel and engines, achieving accelerations no chemical rocket could match. It's the ultimate division of labor. Let planets handle the heavy lifting while the crafts themselves become minimalist marvels, designed only to ride the beam and survive the abyss. Of course, scaling this up to 100 gigawatts means confronting problems no one's ever solved. Current high-energy lasers top out at mere megawatts, and even those require massive cooling systems to avoid melting their own components. The Starshot array would need revolutionary advances in photonics, materials, and energy storage, possibly leveraging breakthroughs in superconducting or metamaterial technologies that don't even exist yet. Then there's the political and logistical nightmare of building what amounts to the most powerful directed energy weapon in history, requiring unprecedented international cooperation to ensure such a system is used only for exploration. Yet if it works, the payoff would rewrite the rules of physics. A successful laser array wouldn't just propel one mission. It could become humanity's first interstellar highway, firing new probes every few years as technology improves. Those photon beams slicing through the void might one day be seen as the umbilical cords tethering our civilization to the stars and the nanocrafts they launch. Just the first sparks of a fire meant to spread across the galaxy, packing an entire spacecraft into a package no heavier than a paperclip sounds impossible until you realize how far nanotechnology has already taken us. These aren't the clunky probes of the past, loaded with fuel tanks and bulky electronics. Project Starshot starships are feats of miniaturization, cramming cameras, sensors, thrusters, and communicators into a speck smaller than a postage stamp. Imagine a spacecraft so tiny you could balance a dozen on your palm, yet capable of surviving the void between stars for decades. This isn't just scaling down existing tech, it's reinventing what a spacecraft even is. The secret lies in breakthroughs that sound like magic but are already in labs today. Take the camera. Traditional lenses are too heavy, so engineers are turning to flat optics, nanostructured surfaces that bend light without glass, thinner than a sheet of graphene. The onboard computer, a single microchip radiation hardened to endure cosmic rays, running on power harvested from the laser beam itself. Even the communication system defies expectations, a laser no wider than a human hair, designed to beam data back to Earth across 4.37 light-years of emptiness. Every component has been stripped to its atomic essentials, optimized for one purpose: to do more with less. Durability is the real killer challenge. Most spacecraft rely on bulky shielding to survive the hazards of space, but a starship has no room for armor. Instead, it borrows tricks from extremophiles organisms that thrive in Earth's harshest environments. The chip's casing might use self-healing nanomaterials, sealing microscopic cracks caused by impacts with interstellar dust. Its electronics could employ redundant circuits, automatically rerouting around damaged pathways. Even the sail, delicate as it seems, might be laced with sensors that detect stress and adjust the laser's beam to prevent tearing. These aren't just gadgets, they're biological-level innovations masquerading as machines. What's most revolutionary isn't the tech itself, but the philosophy behind it. For decades, space exploration meant bigger, heavier, costlier. Starshot flips that script, proving that sometimes the mightiest journeys begin with the smallest steps. Each starship is a bet that we can trade brute force for elegance, that the universe rewards those who work with its laws rather than against them. And if even one of these tiny ambassadors makes it to Alpha Centauri, it won't just send back data. It'll send back proof that humanity's future among the stars might be written not in rocket exhaust but in light. Sending a nanocraft to Alpha Centauri is only half the battle. The real test comes when it's time to phone home. Picture this: a device the size of a thumbtack drifting past an alien star system, trying to beam data across 4.37 light-years of interstellar static. The signal it sends would be so faint that by the time it reaches Earth, it would carry less power than a lightbulb's glow spread over thousands of miles. Yet somehow, we'd need to detect and decode that whisper from the cosmos. This isn't just a technical hurdle, it's a physics-defying feat that demands reimagining communication itself. The most promising solution, a laser no wider than a pencil lead, mounted on the nanocraft, pulsing focused beams of light back toward our solar system. Unlike radio waves, which disperse into noise over interstellar distances, laser light stays tightly bundled, maximizing the chances of reaching Earth intact. But even with this precision, the challenges stack up fast. The spacecraft's laser would need to aim with near-perfect accuracy, aligning its beam with receivers on Earth despite drifting at a fraction of light speed. Imagine trying to hit a bullseye on a dartboard from across a continent while riding a roller coaster. That's the level of precision required. And then there's the problem of power. With only minimal energy harvested from the craft's tiny nuclear battery or stored during its initial laser boost, every photon counts. Engineers are exploring tricks like data compression so extreme it'd make today's smartphones blush, stripping images and measurements down to their most essential bits. The probe might not send raw footage of Alpha Centauri's planets, but instead transmit mathematical summaries distilling landscapes into spectral fingerprints or atmospheric compositions into code. But the true marvel lies in the receiving end. To catch these faint laser pulses, Earth would need a network of telescopes acting like a giant cosmic ear. Facilities like the Very Large Telescope in Chile or future observatories with kilometer-wide mirrors could serve as collection points, their instruments tuned to detect the specific wavelength of the nanocrafts laser. Even then, the signal would be buried in background noise from stars, cosmic rays, and even Earth's own atmosphere. Advanced algorithms would sift through the chaos, identifying the probe's faint pattern like picking out a single voice in a roaring stadium. Timing adds another layer of complexity. With the probe zipping past its target at a fifth of light speed, it might have only minutes to gather data and transmit before vanishing into the void. That means every second of communication must be orchestrated with atomic clock precision, ensuring Earth's receivers are listening at the exact right moment. Miss the window and decades of effort evaporate into silence, yet if it works, the payoff would be unprecedented. That faint laser signal, traveling for over 4 years through empty space, could carry the first close-up images of an exoplanet's surface, or readings of its atmosphere hinting at chemistry we've never seen. It's a reminder that exploration isn't just about reaching new places, it's about bringing pieces of them back to us. And in that faint pulse of light, humanity might finally find proof that we're not just observers of the cosmos, but participants in its grand story. Powering Project Starshot's laser array would demand more electricity than some small nations. 100 gigawatts enough to keep 10 million homes lit must surge through the system in bursts lasting mere minutes, requiring energy storage solutions that don't yet exist at this scale. Traditional power grids can't handle spikes like this without buckling, so the project's architects are eyeing radical alternatives. Imagine fields of solar panels stretching across deserts, paired with banks of next-gen batteries designed to discharge their entire capacity in a single blistering surge. Or offshore wind farms, their turbines sync to the laser's firing schedule, feeding energy directly into the array during peak wind conditions. The goal isn't just generating clean power, but mastering its timing, harnessing renewable energies, intermittent flows to fuel precision interstellar launches. But Earth-based solutions might only be the beginning. Some researchers propose tapping space-based solar power, where orbital collectors harvest sunlight unfiltered by atmosphere, beaming it down as microwaves to laser sites below. Unlike ground installations limited by nightfall and weather, these orbital farms could operate around the clock, converting sunlight into a near-constant energy stream. It's a concept with roots in the 1970s, when physicist Gerard O'Neill first sketched solar satellites as futuristic power plants. Today, private ventures are testing prototypes, suggesting the idea isn't as far-fetched as it sounds. For Starshot, such a system could turn the sun itself into a cosmic charging station, its energy funneled into missions that leap toward the stars. The infrastructure challenges, though, are Herculean. Building the laser array alone would require thousands of high-emission modules, each needing flawless alignment and cooling to prevent meltdowns during operation. Then there's the power storage puzzle. Lithium-ion batteries, even in massive quantities, discharge too slowly for the laser's needs. Alternatives like superconducting magnetic energy storage, where electricity circulates in near-lossless loops until needed, could provide the necessary burst, but these technologies remain experimental. And let's not forget the political dimension. A gigawatt-scale laser, even for peaceful purposes, might raise arms control concerns, demanding unprecedented international transparency to avoid triggering global tensions. Yet the very audacity of these hurdles hints at Starshot's hidden value. Just as the Apollo program birthed innovations from freeze-dried food to integrated circuits, this project could accelerate breakthroughs in energy storage, photonics, and orbital infrastructure. The laser array wouldn't just launch probes, it might catalyze a new era of clean energy systems, their ripple effects transforming life far beyond space exploration. So while the power requirements seem insurmountable today, they represent not just a barrier but a beacon, one that could guide humanity toward mastering energy on a planetary scale. And if we succeed, The same technologies that send sailcraft to Alpha Centauri might one day power our cities, proving once again that the boldest dreams often light the way to practical revolutions. The clock is ticking for Project Starshot, not just in cosmic terms, but in human ones. When the team says they want to reach another star within a generation, they're gambling on a timeline that dances between breathtaking ambition and sobering reality. Picture this: by the 2030s, we might see the first prototype light sails unfurling in low Earth orbit, testing how these featherweight structures handle the violence of laser acceleration. A decade later, perhaps a full-scale demonstrator could make a high-speed dash to the outer solar system, proving the concept works beyond theory, and if all goes perfectly. By the 2060s, a fleet of nanocrafts might finally lift off on their one-way journey to Alpha Centauri. That's the dream scenario, a 40-year sprint from lab to launchpad. But is it realistic or just wishful thinking wrapped in scientific optimism? History offers both hope and caution. The Apollo program went from Kennedy's speech to moon landing in under 9 years, proving that with enough political will and funding, humanity can achieve the seemingly impossible. But Starshot isn't racing against a Cold War rival, it's battling physics itself. Every subsystem, from the lasers to the sails to the communication chips, requires breakthroughs that haven't yet left whiteboards. Unlike Apollo, which built on existing rocket technology, Starshot demands entirely new infrastructures. There's no guarantee materials strong enough for the sail or lasers powerful enough for propulsion will be ready when the calendar hits 2050. Then there's the money problem. Even with billionaires like Yuri Milner backing the project, estimates suggest developing the full laser array could cost tens of billions, more than the GDP of some nations. Traditional space funding, spread across decades of government budgets, won't cut it here. Starshot needs sustained investment from private and public sectors simultaneously, a feat easier said than done when economic priorities shift with every election cycle. One year's budget surplus could vanish the next, leaving critical research stranded. Perhaps the most human hurdle of all is patience. Generational projects ask people to invest in futures they might not live to see. The scientists drafting Starshot's first proposals could retire before the first prototype flies. Today's engineering students might be gray-haired by launch day. That psychological gap between inspiration and payoff has killed grand visions before. But here's the counterpoint: every milestone along the way could revolutionize other fields. The same lasers that propel interstellar probes might also zap space debris or beam clean energy across continents. Miniaturized sensors developed for nanocrafts could transform medicine or environmental monitoring. So can it really happen in our lifetime? The answer depends less on physics than on something far messier: collective human determination. If funding holds, if technologies converge, if society decides the stars are worth reaching for, then yes, a 2060s launch isn't just possible, it's inevitable. But those are big ifs. What makes Starshot extraordinary isn't the certainty of success, but the refusal to accept failure as predetermined. Even if the timeline slips, even if the first probes don't launch until the 2080s, the mere attempt redefines what we consider achievable. After all, generations aren't just measures of time, they're vessels for passing the torch. And this project, more than any other, proves that torch can burn across the light years. $5 to $10 billion isn't just a price tag, it's a statement about how we value the future. That's the estimated cost to turn Project Starshot from blueprint to reality, a figure that lands somewhere between a Hollywood blockbuster franchise and a single aircraft carrier. To put it in perspective, NASA Mars Perseverance rover cost about $2.7 billion, while the James Webb Space Telescope eclipsed $10 billion after decades of development. Starshot's budget sits in that same league, but with a crucial difference: it's not government money driving this vision. Instead, it's the audacity of private backers like Yuri Milner, whose breakthrough initiatives have already poured over $100 million into preliminary research. This shift from taxpayer-funded programs to billionaire philanthropy marks a seismic change in how humanity tackles cosmic-scale challenges. But can private funding alone shoulder this burden? Milner's resources are vast, yet even his fortune would stretch thin covering the full cost. That's where unconventional partnerships come into play. Imagine a Kickstarter campaign not for a smartwatch or video game, but for humanity's first starship. Crowdfunding interstellar travel might sound absurd until you consider that the original Star Trek series was saved by fan-led letter campaigns, or that the Arecibo Observatory once thrived on public donations. If millions of people contributed the price of a coffee, those microtransactions could add up to macro progress. The emotional appeal is undeniable. For the cost of a streaming subscription, you could literally own a piece of the mission that touches another star. International collaboration offers another path. Unlike Cold War space races where superpowers hoarded technology, Starshot thrives on shared knowledge. Countries without traditional space programs could contribute specialized expertise, Switzerland's precision engineering, Japan's miniaturization prowess, or Chile's prime telescope real estate. Pooling resources could democratize the project, transforming it from a billionaire's passion into a global milestone. The International Space Station proved rivals can cooperate in orbit. Why not extend that model to interstellar exploration? Yet the economic feasibility debate isn't just about raising funds. It's about opportunity costs. Critics argue that $10 billion could vaccinate millions, build resilient cities, or solve pressing terrestrial crises. But history shows that frontier technologies often spin off unexpected benefits. The Apollo program gave us MRI machines and water filters. Starshot's lasers might revolutionize clean energy or deep space communication. The money wouldn't vanish into a black hole. It would supercharge industries, create jobs, and inspire generations to invest in science. The real question isn't whether we can afford Starshot. It's whether we can afford not to try. In a century obsessed with quarterly profits and short-term gains, this project forces us to think in lifetimes rather than fiscal years. That budget breakdown spread across decades and nations isn't an invoice. It's a down payment on immortality. Starshot isn't the only game in town when it comes to reaching the stars, just the most daring. NASA has toyed with interstellar ambitions for decades, focusing on slower but steadier approaches. Take their solar cruiser concept, a massive sail designed to ride sunlight alone, no lasers required. While it could theoretically reach the outer solar system, sunlight's gentle push would take centuries to approach relativistic speeds. Then there's nuclear pulse propulsion, a Cold War-era idea that sounds like something from a doomsday manual. Detonate atomic bombs behind a spacecraft, letting the shockwaves propel it forward. Calculations suggest it could hit 5% light speed, fast, but still an 80-year trip to Alpha Centauri, with the added baggage of radioactive controversy. Private ventures have thrown their hats in the ring too. The Tau Zero Foundation champions antimatter propulsion, where matter-antimatter annihilation releases pure energy. In theory, it's the ultimate fuel, but storing even a gram of antimatter requires magnetic traps so precise they'd make a Swiss watch look crude. Meanwhile, Breakthrough Initiative's own sister project, Breakthrough Watch, focuses on telescopes rather than probes, scanning Alpha Centauri for biosignatures from the safety of Earth's orbit. Each of these ideas has merit, but they share a common flaw. They're either too slow, too unpredictable, or too dependent on technologies that don't exist yet. What sets Starshot apart isn't just speed, it's scalability. While nuclear or antimatter engines require breakthroughs in containment and energy efficiency, laser propulsion builds on existing photonics and materials science. The same phased array lasers that could push a nanocraft might one day power orbital cleanup missions or asteroid deflection systems. Even the light sail concept has pedigree. Japan's Ikaros probe proved solar sailing works in interplanetary space, and NASA NEA Scout aims to use a sail for lunar exploration. Starshot simply takes these proven principles and cranks them to 11, swapping passive sunlight for a targeted beam of raw power. That's not to say competing projects lack value. Nuclear propulsion, for all its challenges, could be the key to crewed missions within our solar system. Antimatter research might unlock energy revolutions far beyond spaceflight. But if the goal is planting humanity's flag, or rather silicon chip, on another star within our lifetime, light sails offer the only roadmap with milestones already in sight. The others are branches on the tree of possibility. Starshot's the trunk, grounded in what we know while reaching for what we've only dreamed. And in the race to the stars, sometimes the boldest shortcut is refusing to take detours. Those first close-up images from Alpha Centauri wouldn't just be pretty pictures, they'd rewrite the textbooks of astronomy. Imagine a photograph of Proxima B's surface, not as a blurry pixel, but with enough resolution to distinguish continents from oceans, clouds from landmasses. For the first time, we'd see an alien world as a place, not just a data point. But the real treasure lies in the details. Spectral analysis of its atmosphere could reveal methane spikes hinting at life, or oxygen patterns suggesting geological activity. Even a barren landscape would be revolutionary, proving whether rocky planets around red dwarfs are hellish wastelands bathed in radiation or hidden oases with protective magnetic fields. Then there's the journey itself. The space between stars isn't empty. It's a soup of cosmic rays, interstellar dust, and hydrogen atoms too sparse to measure from Earth. Starshot's probes would act like interstellar weather stations, sampling this medium firsthand. Picture detecting microscopic dust grains that originated in supernova billions of years ago, or mapping magnetic fields that twist between stars, data impossible to gather from our solar system. These readings could solve mysteries like the galactic distribution of lithium or the nature of dark matter's gravitational fingerprint, but the most profound payoff might be statistical. Right now, we're guessing whether Earth-like planets are cosmic flukes or commonplace. Starshot could settle the debate by surveying not just Proxima b, but any undiscovered worlds lurking in the Alpha Centauri system. Finding even one more planet, especially in the habitable zone of Centauri A or B, would double our sample size overnight, and if multiple systems prove to have rocky worlds. That's game-changing evidence for the ubiquity of life's potential playgrounds. Astrobiologists are already salivating at the thought of atmospheric spectra. On Earth, we detect life by its chemical fingerprints: oxygen from photosynthesis, methane from microbes. A single anomalous gas ratio in Alpha Centauri's data could ignite a scientific earthquake. But even negative results would be priceless. Proving a sun-like star's habitable zone doesn't guarantee habitability would force us to rethink everything from planetary formation to the Fermi paradox. This mission isn't just about adding to our knowledge, it's about shattering paradigms. Every measurement, every pixel would force us to confront realities that no telescope, no simulation, no theory could predict. Because when you're dealing with alien star systems, the only thing more thrilling than finding what you expect is discovering what you never imagined. Sending even a speck of human technology to another star isn't just an engineering challenge, it's a moral dilemma wrapped in cosmic-scale uncertainty. Consider the possibility that Alpha Centauri hosts life, perhaps microbial organisms clinging to the icy shadows of Proxima b. A stray microbe hitchhiking on one of our nanocrafts, surviving the vacuum and radiation of interstellar space, could become an invasive species on an alien world. It's the ultimate contamination risk, turning humanity's first interstellar message into a biological time bomb. The same protocols that sterilize Mars rovers to protect potential Martian ecosystems would need to be multiplied 1,000-fold for Starshot, requiring sterilization techniques so extreme they might not even exist yet. But contamination cuts both ways. Some ethicists argue that refraining from exploration out of caution could be its own kind of failure, a surrender to fear that keeps us forever isolated. After all, nature isn't static. Meteorites have been shuttling material between planets for billions of years. If life exists on Proxima b, it's likely already endured bombardments from cosmic debris. Would our nanocraft really pose a greater threat than the natural exchange of asteroids and comets? The debate echoes terrestrial conservation battles where the line between preservation and paralysis blurs. Do we lock away fragile ecosystems or accept that responsible interaction is the price of understanding? Then there's the allocation problem. In a world grappling with climate disasters, inequality, and pandemics, does spending billions to reach the stars border on negligence? Critics see Starshot as a distraction, a billionaire's vanity project while Earth burns, but history suggests exploration rarely happens in tidy sequences. The Renaissance didn't wait for plagues to end before funding Da Vinci's inventions. The digital age didn't pause until global poverty was solved. Human progress isn't a zero-sum game. The technologies spun off from Starshot, advanced lasers, ultra-efficient energy systems, nanomaterials, could address terrestrial crises in ways we can't yet predict. The same photovoltaic breakthroughs that power light sails might one day revolutionize clean energy grids. Perhaps the most profound question isn't can we go, but should we? Space exploration has always been a mirror for our values. The Apollo missions projected Cold War rivalry into the cosmos. Modern Mars rovers carry names chosen by school children. Starshot forces us to ask what story we want to tell about humanity in this century. Are we caretakers too cautious to reach beyond our cradle, or pioneers willing to risk contamination for the chance to know we're not alone? There's no easy answer. Only the certainty that how we navigate these questions will define us long after the first probes arrive at Alpha Centauri. And let's not forget the silent stakeholders, future generations. If we avoid interstellar exploration out of fear or frugality, what legacy does that leave? A universe full of questions we refuse to ask, or worse, a civilization that chose safety over wonder, only to wither on a planet it never learned to escape. The ethics of Starshot aren't just about today's dilemmas. They're about planting trees whose shade we'll never sit under, trusting that those who come after us will understand why we reached for the stars while keeping our conscience clear. It's a balance as delicate as the sails themselves, pulled between ambition and humility, between the dream to explore and the duty to protect. Every groundbreaking idea faces skeptics, and Project Starshot is no exception. While the vision of reaching another star within decades electrifies imaginations, physicists and engineers have raised legitimate concerns that deserve attention. Take laser dispersion, the challenge of keeping a beam tightly focused over interstellar distances. Critics argue that even with phased array technology, tiny imperfections in the laser or atmospheric interference could scatter the beam's energy, leaving the light sail stranded without enough push. It's like trying to hit a speeding bullet with a second bullet from 1,000 miles away, where even a micron-sized miscalculation spells failure. The math suggests it's possible, but no one's ever built a system precise enough to prove it. Then there's the nightmare scenario of interstellar debris. At 20% light speed, a collision with a grain of sand, or worse, a pebble, would unleash energy comparable to a nuclear blast relative to the nanocraft's tiny mass. Engineers speculate about embedding self-healing materials or creating microshields, but space is vast and odds are unforgiving. Some models suggest a single mission might need thousands of probes launched in waves, accepting that most will be obliterated by unseen hazards. It's less like sending a spaceship and more like scattering confetti into a hurricane, hoping a few strands make it through. Reliability over decades is another sticking point. Modern satellites often fail within years due to radiation damage or mechanical wear. Starshot's probes must survive 20 years of cosmic bombardment with zero maintenance. While radiation-hardened chips exist, no one's tested them under such prolonged, extreme conditions. And if a probe arrives at Alpha Centauri only to find its cameras fried or its transmitter dead, the mission becomes a trillion-dollar silent movie. Even the project's timeline draws raised eyebrows. History's most complex space missions, Cassini, JWST, Curiosity, took decades from concept to launch. Starshot aims to leapfrog those timelines while tackling problems far more exotic. Optimists call it ambitious, realists call it a gamble. Yet these critiques aren't reasons to abandon the dream, they're a to-do list for making it real. Every objection is a puzzle waiting for a solution, and humanity's greatest leaps have always started with someone refusing to accept impossible as the final answer. The skeptics aren't enemies of progress, they're vital collaborators, stress-testing the vision until it's sturdy enough to survive the journey. LightSail 2 wasn't just a successful mission, it was a quiet revolution. In 2019, this shoebox-sized spacecraft unfurled a shimmering sail thinner than a human hair, catching sunlight like a cosmic kite. For over 3 years, it rode photons alone, adjusting its orbit without a single drop of fuel. The data it beamed back wasn't just promising, it proved light sails aren't sci-fi fantasies, but viable propulsion systems. Every tweak of its reflective surfaces, every maneuver executed by angling the sail like a windsurfer's canvas, gave engineers something priceless, real-world evidence that solar sailing works beyond theory. Starshot's designers pored over these results, noting how even subtle wrinkles in the sail's material could alter performance, or how micrometeoroid impacts tiny but relentless, required redundant systems to maintain stability. But LightSail 2 was just the opening act. Japan's Ikaros probe had already made history in 2010 as the first spacecraft to demonstrate solar sail propulsion between planets, complete with thin-film solar cells embedded in its sail to generate power. Then there's NASA NEA Scout, set to ride a solar sail to a near-Earth asteroid, proving the technology can handle precise navigation. These missions share a common thread, they're stepping stones, each tackling a piece of the puzzle Starshot needs to solve. LightSail 2 mastered the basics of photon propulsion, Ikaros integrated power generation, and NEA Scout is testing deep space agility. Together, they form a blueprint for how to scale up to interstellar speeds. The lessons aren't all technical. LightSail 2 team discovered something unexpected: the psychological power of visibility. From Earth, the sail occasionally flared brighter than Venus as it caught the sun, a gleaming speck anyone could spot with binoculars. That tangibility, that connection between a groundbreaking technology and the naked eye, became a rallying cry for public engagement. Starshot's architects took note. Their nanocrafts may be invisible to stargazers, but the laser array itself, a kilometers-wide installation glowing against the night, could become a modern-day lighthouse of Alexandria, a beacon of human ambition visible from orbit. Yet for all these triumphs, the gulf between solar sailing and laser propulsion remains vast. Sunlight is gentle, a gigawatt laser is anything but. Early lab tests reveal the brutal physics at play. Even the thinnest materials vaporize under such intensity unless engineered to reflect 99.9% of the beam. That's why researchers are now stress-testing prototype sails in vacuum chambers, bombarding them with laser pulses to simulate the onslaught they'd face during acceleration. Some designs use nanostructured surfaces that scatter heat like a mirror scattering light, while others experiment with self-cooling mechanisms inspired by termite mounds' natural ventilation. Every scorched sample, every torn edge, is a clue leading toward a sail that won't just survive the journey, but conquer it. What's emerging from these experiments is a paradox. The sails must be impossibly delicate to minimize weight, yet indestructibly robust to endure forces no spacecraft has ever faced. It's like trying to build a spiderweb strong enough to stop a bullet. But here's the breakthrough: we're learning failure is part of the process. LightSail 2 occasional wobbles, Ikaros navigation hiccups, these aren't setbacks but textbooks written in real time. Every glitch teaches us more about stitching the fabric of tomorrow's starships. And with each test, whether in orbit or underground labs, humanity inches closer to a truth once reserved for poets and dreamers. The stars aren't just for watching. They're for reaching. No mission as ambitious as Starshot can go it alone, and that's where space agencies and private giants step in. NASA and the European Space Agency have decades of experience wrestling with the brutal challenges of deep space, from radiation hardening to interstellar communication. Their expertise could be the missing puzzle piece that transforms Starshot from whiteboard equations to hardware. Imagine NASA, a jet propulsion laboratory, the team behind interplanetary probes like Voyager and Perseverance, collaborating on nanocraft navigation systems. Or ESA's deep space antenna network, already used to talk to missions billions of miles away, adapted to catch those faint laser pulses from Alpha Centauri. These partnerships wouldn't just share knowledge, they'd multiply Starshot's chances of success by tapping into institutions that have spent half a century learning to survive the void. Then there's the private sector's explosive potential. SpaceX's Starship, with its massive payload capacity, could theoretically loft the laser array components into orbit for assembly, bypassing Earth's distorting atmosphere entirely. Blue Origin's advanced solar power technologies might solve the energy puzzle. Even companies like L3Harris, which builds military-grade lasers, could repurpose their precision beam control systems for interstellar missions. The beauty of these collaborations lies in their symbiosis. Starshot offers a visionary goal, while industry partners bring production scaling and real-world testing grounds. But this isn't just about borrowing expertise. Space agencies have skin in the game too. NASA's upcoming Interstellar probe, slated to launch in the 2030s, aims to travel 2,000 astronomical units beyond our solar system, a perfect testbed for Starshot's navigation and communication tech. ESA's proposed laser interferometer space antenna could evolve into a receiver for interstellar data streams. When multiple players invest, the financial burden lightens for everyone, and breakthroughs in one program ripple across others. The most exciting prospect, seeing these partnerships reframe what's possible. Government agencies often move cautiously, constrained by budgets and political cycles. Private companies chase profits, sometimes at the expense of long-term vision. But united under Starshot's audacious timeline, their combined strengths could shore up the decades of incremental progress usually required for space tech. It's the difference between building a car alone in your garage versus joining forces with Ferrari's engineers and Tesla's battery experts. The destination stays the same, but the journey gets exponentially smoother. Of course, collaboration isn't without friction. Proprietary tech, conflicting priorities, and bureaucratic red tape could slow integration. Yet history shows that when humanity faces grand challenges, from the International Space Station to the Large Hadron Collider, we're capable of aligning our efforts across borders and balance sheets. Starshot might just be the catalyst that proves space exploration's next giant leap won't belong to any one nation or corporation, but to the collective genius of a species reaching for the stars. Navigating the interstellar void isn't like driving a car with GPS. There's no roadside assistance, no real-time updates, and certainly no chance for human hands to take the wheel. At 20% light speed, even radio signals take over 4 years just to reach Alpha Centauri, making instant communication impossible. That's where artificial intelligence steps in, transforming these nanocrafts from passive projectiles into autonomous explorers capable of making life or death decisions in the blink of an eye. The AI aboard these probes won't just follow a pre-programmed path. It'll constantly reassess threats, recalculate trajectories, and even prioritize scientific targets, all while hurtling through space at speeds that would turn a grain of dust into a deadly projectile. Machine learning algorithms trained on petabytes of simulated space data will act as the probe's cosmic instincts, Picture a neural network that's digested every known variable of interstellar travel: the gravitational pull of passing stars, the density of dust clouds, the statistical likelihood of micrometeoroid swarms, then distilled that knowledge into split-second judgments. When an unexpected debris field appears, the AI won't freeze. It'll compare the obstacle to thousands of simulated scenarios in its memory, choosing evasion maneuvers with the precision of a chess grandmaster anticipating moves 10 turns ahead. Some systems might even employ swarm intelligence, where multiple probes communicate briefly during flight to share hazard maps, creating a collective mind far smarter than any individual craft. But trajectory optimization is only half the battle. These AIs must also become master scientists on the fly. During its brief flyby of Alpha Centauri, a probe might have mere minutes to decide whether to focus its camera on Proxima B's twilight zone for potential liquid water or scan Centauri A's asteroid belt for planetary formation clues. Reinforcement learning models algorithms that improve through trial and error could make those judgment calls by weighing decades of astrobiological research against real-time sensor data. It's like training a robotic Charles Darwin to recognize evolutionary signatures in alien landscapes, then giving it complete autonomy to pursue discoveries. Yet autonomy comes with terrifying risks. A single software glitch could misinterpret a star's glare as an obstacle, triggering unnecessary course corrections that waste precious energy. That's why engineers are exploring hybrid systems where multiple AI models cross-check each other, voting on critical decisions like a miniature scientific council. Some designs even include kill switches, preset limits that prevent the AI from straying too far from its core mission parameters, ensuring these microscopic explorers stay focused despite the cosmic wonders tempting them off course. The true test of this technology won't happen in a lab, but in the cold expanse between stars. Out there, with no human to press reset, these artificial minds will become humanity's first truly independent interstellar ambassadors. Their success or failure won't just determine whether we see Alpha Centauri up close. It'll prove whether machines can carry our curiosity across the light years, thinking and adapting where we cannot follow. And if they succeed, the AI guiding these nanocrafts might just become the prototype for all future deep space explorers, silent, vigilant, and endlessly resourceful in the face of the unknown. At 20% the speed of light, even a speck of dust becomes a deadly bullet. Interstellar space might look empty from Earth, but it's actually littered with microscopic hazards, dust grains left over from ancient supernova, flecks of asteroid collisions, and hydrogen atoms so sparse they're barely there, yet moving fast enough to rip through unprotected materials. For Starshot's nanocrafts, this isn't just a nuisance, it's an existential threat. A single grain weighing less than a snowflake could strike with the energy of a hand grenade relative to the probe's tiny mass, vaporizing critical systems in an instant. And that's before accounting for cosmic rays, high-energy particles streaming from distant stellar explosions, capable of frying electronics over time like invisible sandblasters. So how do you armor something that can't carry armor? Traditional shielding would weigh too much, negating the whole advantage of being featherlight. Instead, engineers are borrowing tricks from nature and nanotechnology. Some designs use graded shields, layers of atomically thin materials like graphene and beryllium that gradually absorb and dissipate impact energy, mimicking the way a balloon's shells distribute force across microscopic structures to prevent cracks. Others propose self-healing materials embedded with microcapsules of liquid polymer that automatically seal punctures, a concept inspired by human blood clotting. But perhaps the most elegant solution is avoidance. Advanced detection algorithms could identify dense dust clouds using miniaturized LiDAR sensors, prompting the probe to adjust its sail angle slightly, just enough to skirt danger without significant speed loss. Cosmic rays present a subtler challenge. Unlike dust impacts, these particles don't announce their arrival with violent explosions. They sneak in silently, flipping bits in computer memory or degrading solar cells over time. To combat this, Starshot's engineers are looking to radiation-hardened chips originally designed for nuclear reactors and military satellites, paired with redundant systems that vote on critical decisions to override corrupted data. Some prototypes even experiment with neuromorphic computing processors that mimic the human brain's fault tolerance by rerouting tasks around damaged circuits. Yet the ultimate safeguard might be numbers. Rather than betting everything on one perfect probe, Starshot could launch hundreds or thousands, accepting that most will succumb to the void. It's a strategy borrowed from deep-sea life where organisms like krill survive predators through sheer volume, applied to interstellar exploration. Each casualty would teach us something, refining designs for the next wave until the odds tip in our favor. What's fascinating is how these solutions blur the line between engineering and philosophy. Protecting something so small against forces so vast forces us to rethink resilience itself. It's not about being invincible, but adaptable, about building probes that expect to be wounded and know how to heal. Because out there in the dark, survival isn't guaranteed by brute strength, but by the wisdom to yield where you must and push forward where you can. And if even a handful of these tiny voyagers make it through, their scars will tell a story far more valuable than any pristine machine could, proof that fragility isn't the opposite of endurance but its crucible. Launching a mission to another star isn't just a physics problem, it's a legal minefield waiting to be navigated. The Outer Space Treaty of 1967, signed at the height of the Cold War, declares space as the province of all mankind, prohibiting any nation from claiming celestial bodies. But here's the catch: the treaty never anticipated private entities sending probes to other solar systems. Who governs a nanocraft sailing toward Alpha Centauri? The country that launched it, the corporation that funded it, or does it become some strange interstellar commons the moment it leaves our solar system? These questions aren't academic. They could determine whether Starshot faces decades of lawsuits or smooth sailing. Then there's the laser array itself, a system so powerful it straddles the line between scientific tool and orbital weapon. Under the Anti-Ballistic Missile Treaty, space-based weapons are heavily restricted, and while Starshot's lasers are designed for propulsion, their sheer power could make arms control experts nervous. Imagine the diplomatic headache if one nation's interstellar ambition is perceived as a thinly veiled missile defense system. The technology might be peaceful, but perception matters when gigawatt beams are involved. This isn't hypothetical. Similar concerns temporarily stalled early laser communication experiments during the Reagan era. International collaboration offers both promise and pitfalls. While pooling resources from multiple countries could accelerate progress, geopolitical tensions could just as easily derail everything. Picture a scenario where a Starshot consortium includes both the United States and China, only for a trade war or territorial dispute to freeze joint operations mid-construction. Space stations have survived political storms through carefully negotiated agreements, but an interstellar mission would require unprecedented long-term commitments. Even data-sharing protocols could become contentious if a probe discovers evidence of alien life. Which nation gets to announce it to the world? Private enterprise adds another layer of complexity. Current space law treats companies as extensions of their home countries, but what happens when a billionaire's pet project starts altering the interstellar environment? There's no precedent for taxing or regulating commercial activity beyond our solar system, yet the lasers and probes could become de facto infrastructure for future missions. Like railway barons of the 19th century, early interstellar trailblazers might wind up controlling access to the stars unless clear frameworks emerge. Perhaps the thorniest issue is planetary protection in reverse. While we worry about contaminating Mars with Earth microbes, Alpha Centauri's potential biosphere raises the opposite concern. What if returning data or future sample missions accidentally bring something back? Current protocols focus on keeping Earth safe from extraterrestrial organisms, but an interstellar mission would need safeguards against both export and import of biological material. The legal framework for this simply doesn't exist yet, leaving scientists and policymakers to wrestle with scenarios that sound like sci-fi plotlines. These challenges aren't deal-breakers, they're growing pains. Every great exploration effort, from the Age of Sail to the International Space Station, has required updating old rules for new realities. What makes Starshot remarkable is how it forces us to think beyond terrestrial squabbles and consider humanity as a collective spacefaring species. The treaties may need revising, the partnerships may require delicate diplomacy, but the alternative, staying forever bound to our solar system by paperwork and politics, is too bleak to contemplate. After all, the stars won't wait for us to settle our differences. They'll keep shining, indifferent to whether we're wise enough to reach them. Successfully reaching another star wouldn't just be a scientific milestone. It would send shockwaves through the very fabric of human culture, rewriting our collective imagination. Think back to 1969, when grainy black and white footage of Neil Armstrong's moonwalk flickered across televisions worldwide. Overnight, the phrase, "one small step," became a universal mantra, proof that the impossible was within reach. Now amplify that impact by orders of magnitude. Images beamed back from Alpha Centauri wouldn't just document alien landscapes, they'd collapse the psychological distance between Earth and the cosmos, making interstellar space feel less like an abstraction and more like a neighborhood we're just beginning to explore. Schools would teach children about Proxima B's mountains and valleys alongside Everest and the Grand Canyon, folding distant worlds into our sense of home. Art would explode with new visions. The Renaissance had its celestial globes. We'd have holographic exoplanetariums. Musicians might compose symphonies using the rhythmic pulses of laser communications from our probes, while filmmakers ditched tired alien tropes for stories grounded in real interstellar data. Imagine a post-Starshot sci-fi where scripts consult actual atmospheric readings from Centauri's planets, swapping green-skinned caricatures for biologically plausible lifeforms shaped by red dwarf suns. Even fashion could absorb the aesthetic designers, riffing on light sail silhouettes or embedding fabrics with microprints of Alpha Centauri's triple-star sunrise. Culture thrives on novelty, and nothing would be more novel than touching another star. The philosophical shift would run deeper still. For millennia, humans saw the stars as untouchable gods or navigational guides. Starshot's success would demystify them, transforming those pinpricks of light into places with geology, weather, and perhaps even biology. Religions might incorporate interstellar discovery into their cosmologies, just as Galileo's telescope forced reinterpretations of celestial dogma. Atheists and believers alike could find common awe in the revelation that our species had bridged the interstellar gulf, not in some distant future but within living memory. The very concept of generation would gain new weight as grandparents who watched the launch share the probe's discoveries with grandchildren born decades later. Historically, breakthroughs in exploration have shattered societal inertia. The moon landing coincided with the civil rights movement and anti-war protests, proving that humanity could aim higher than earthly conflicts. Starshot's triumph might similarly reframe global priorities, making petty nationalism seem archaic against the backdrop of interstellar achievement. Could anyone cling to border disputes when telescopes deliver daily reminders of our shared fragility on a pale blue dot now capable of touching other suns? The project's international collaboration, scientists from rival nations working toward a common cosmic goal, could become a template for solving terrestrial crises, from climate change to pandemics. Yet the most profound change might be invisible: the quiet dismantling of mental barriers. Before 1957, space was a realm for gods and fiction. After Sputnik, it became a human domain. Starshot would complete that transition, proving that the vast interstellar ocean isn't just navigable, it's ours to cross. Future generations might grow up assuming star travel is inevitable, just as today's youth take smartphones and gene editing for granted. And that's the true cultural revolution, not just doing something extraordinary, but making it feel ordinary. The moon landing taught us we could leave our planet. Starshot would teach us we belong among the stars. Picture a future where Starshot's first successful probe is just the opening salvo in an interstellar revolution. That single nanocraft, smaller than a deck of cards, could ignite a chain reaction not just of discovery, but of expansion. Within decades, fleets of upgraded successors might be streaming toward nearby stars, each wave more advanced than the last. Early models could deploy relay stations along the way, forming a celestial network to boost signals back to Earth. Later versions might carry more sophisticated instruments, drills to sample asteroid belts around other suns, or micro-rovers designed to detach and explore planetary surfaces. This wouldn't just be exploration, it'd be infrastructure, quietly laying the groundwork for humanity's next act. Now consider the colonization angle. While Starshot's current probes are too tiny to carry human passengers, their descendants could evolve into something more ambitious. Imagine scaled-up versions with 3D printers capable of constructing basic shelters from local materials using nanoscale assembly. They'd arrive decades ahead of any crewed mission, transforming inhospitable worlds into outposts ready for human arrival. These autonomous pioneers might extract water from icy moons, synthesize oxygen from alien soils, or even build landing pads using molten regolith, all before the first astronaut ever leaves Earth. It's the ultimate contingency plan. If our planet ever faces an existential threat, these scattered footholds could offer a lifeline for civilization. Then there's the elephant in the cosmos: extraterrestrial life. Starshot's probes wouldn't just hunt for microbial fossils, they'd carry sensors tuned to detect techno-signatures, evidence of intelligence. Suppose one flyby captures grid-like patterns on a distant world, or detects atmospheric pollutants suggesting industrial activity. That single data point could rewrite humanity's place in the universe. Even null results would be profound. If we scan a dozen habitable zone planets and find zero signs of civilization, the Fermi paradox grows darker. Are we alone? Or are we simply early to the party, but the deepest implications might be psychological? For millennia, humans have worshipped, feared, and dreamed about the stars while fundamentally viewing them as untouchable. A successful Starshot legacy would shatter that mental barrier forever. When children learn that probes are en route to 5 nearby stars with 10 more launching next year, space stops being a backdrop and becomes a destination. That shift in consciousness could be more transformative than any technology. Exploration isn't just about what's out there, it's about who we become when we dare to reach. And that's the true promise lurking in these microscopic probes. They're not just cameras or sensors, they're seeds. Each one carries the potential to reshape our future, whether by finding neighbors among the stars or proving we'll need to build our own. The first steps are always small, but as any explorer knows, it's the act of stepping that changes everything. Failure isn't just a possibility for Project Starshot, it's practically guaranteed in some form. When you're dealing with technology this cutting edge, pushing the boundaries of physics and engineering, something will go wrong. The real question isn't if but how, and more importantly, what we learn when it does. Take the laser propulsion system, for example. Even with perfect calibration, atmospheric turbulence or a minuscule misalignment could scatter the beam, leaving a nanocraft drifting without enough acceleration to escape the solar system. It's like trying to shoot a rubber band across a football field while standing on a wobbling ladder, except the rubber band costs millions of dollars and carries humanity's interstellar dreams. Then there's the haunting specter of silence. Imagine a probe surviving the 20-year journey only to have its transmitter fail, rendering all that data inaccessible. Or worse, discovering too late that the laser communication system wasn't powerful enough to punch through interstellar interference. These aren't abstract fears. History is littered with missions that vanished without a whisper. The Beagle 2 lander on Mars, the Phobos Grunt probe spiraling into the Pacific space exploration, has always been a gamble where the house holds most of the cards. But here's where Starshot flips the script. Its contingency plans are baked into its very design. Unlike traditional monolithic missions where a single failure can spell disaster, this project embraces redundancy. Launching hundreds or even thousands of nanocrafts isn't just about improving odds, it's about accepting that most won't make it, and that's okay. Think of it like dandelion seeds scattered to the wind. A few might land on fertile soil, the rest become part of the experiment. Each lost probe provides critical data. Maybe one reveals how interstellar dust erodes sails at high speeds, while another teaches us how cosmic radiation corrupts onboard memory over decades. Failure isn't the end, it's the tuition we pay for interstellar knowledge. The backup strategies read like a mad scientist's playbook. Some probes might carry emergency power reserves, allowing them to reboot systems if primary energy sources fail. Others could deploy miniature radio beacons as last-ditch signaling devices, trading efficiency for survivability. Engineers have even toyed with sacrificial shields, disposable layers that absorb debris impacts before they reach critical components, like a knight discarding damaged armor mid-battle. And if all else fails, there's the ultimate contingency: time. Probes drifting silently through space might one day be recovered by future civilizations, human or otherwise, bearing silent testimony to our first fumbling steps beyond the solar system. What's most striking about these plans isn't their complexity, but their philosophy. Starshot's architects understand that in the face of such staggering challenges, perfection isn't the goal, progress is. The Voyager probes, now drifting beyond the heliosphere, were designed in the 1970s with technology less powerful than a modern calculator. They're riddled with flaws by today's standards, yet they revolutionized our understanding of the outer planets. Starshot follows that same pioneering ethos: try, fail, adapt, and try again. Because the alternative, never trying at all, is the only true failure, and if even one nanocraft succeeds, that's enough to light a beacon that could guide humanity for centuries to come. Project Starshot isn't just a mission, it's a worldwide classroom without walls. From the moment the first laser fires, this endeavor has the power to ignite curiosity in ways no textbook ever could. Imagine kids in Tokyo, Nairobi, or Rio tracking a fleet of nanocrafts the size of postage stamps racing toward Alpha Centauri, knowing those tiny probes were designed by human hands. That's the magic of Starshot. It turns abstract equations into tangible adventure, transforming astrophysics from a niche subject into a shared human story. Schools are already capitalizing on this excitement. Breakthrough Initiatives, the organization behind Starshot, partners with STEM programs to bring interstellar concepts into classrooms through interactive modules. Students aren't just learning about light sails, they're designing miniature versions in science fairs, competing to see whose sail can catch the most photons in a vacuum chamber. Universities host Starshot challenges, where teams brainstorm solutions to real mission hurdles like dust shielding or laser calibration. These aren't hypothetical exercises. Some winning ideas have actually made their way into engineering white papers, proving that inspiration isn't a one-way street. Citizen scientists play an equally vital role. Amateur astronomers are being prepped to help monitor the laser array's test firings, using backyard telescopes equipped with special filters. There's even talk of an app that would let anyone with a smartphone contribute to signal detection, crowdsourcing the search for Alpha Centauri's faint laser pulses amid cosmic noise. It's a modern twist on the age-old tradition of stargazing, where hobbyists once catalogued comets but now help decode interstellar telemetry. Museums and planetariums are joining the movement too. The Smithsonian's upcoming Starshot exhibit features a scale model of a nanocraft suspended in a laser web, letting visitors walk through a beam path to grasp the sheer precision required. Meanwhile, educators are using Starshot's timeline 20 years to another star to teach patience and long-term thinking. A student who starts following the mission in middle school could witness its climax as a young professional, bridging generations through shared anticipation. The project's cultural ripple effects are just as profound. Documentaries chronicling the mission's highs and lows have become streaming hits, while podcasts dissect each technical milestone like sports commentators analyzing a championship game. Social media campaigns like #message to Alpha Centauri invite the public to contribute digital time capsules that could one day be encoded into probe transmissions, because exploration isn't just about sending machines. It's about sending our collective hopes. What makes Starshot's public dimension unique is its democratizing spirit. Unlike historic space races dominated by government elites, this mission thrives on grassroots energy. Whether it's a teenager 3D printing sail prototypes or a retired engineer volunteering to analyze telemetry data, the invitation stands. The stars aren't just for experts. They're for anyone willing to look up and wonder. And in that inclusive vision lies Starshot's quiet revolution, not just advancing technology, but reigniting our primal urge to explore, one curious mind at a time. Powering a laser array capable of propelling nanocrafts to another star isn't just an engineering challenge, it's an environmental balancing act on a planetary scale. Picture this, a network of lasers consuming 100 gigawatts per launch, briefly drawing more power than some industrialized nations. If that energy came from fossil fuels, each interstellar shot could pump millions of tons of carbon dioxide into the atmosphere, an ironic twist where reaching the stars accelerates the degradation of our own planet. The math gets even starker when considering Starshot's envisioned fleet of probes. Without clean solutions, this could become space exploration's dirty secret, trading cosmic breakthroughs for terrestrial consequences. But what if the same lasers driving interstellar ambition could also pioneer Earth's energy revolution? Researchers envision coupling the array with vast renewable farms, fields of solar panels spanning deserts, or offshore wind turbines synced to launch windows. Solar energy is particularly compelling. A single hour of sunlight hitting Earth holds enough energy to power civilization for a year. Harnessing even a fraction could fuel lasers without carbon guilt. The catch: renewables' intermittent nature clashes with the need for precise, on-demand bursts. Batteries capable of storing gigawatt-hours exist only on paper, leading engineers to explore alternatives like supercapacitors that dump energy in violent surges, or flywheel systems spinning at near-vacuum frictionlessness. Space-based solar power offers an even more elegant fix. Imagine orbital mirrors concentrating sunlight onto photovoltaic arrays unfiltered by atmosphere, beaming microwaves down to laser sites. Unlike ground solar hampered by nightfall, these orbital generators could harvest constant energy, turning the sun itself into a cosmic gas station. Japan's 2015 wireless power transmission experiment proved energy can travel kilometers through air without wires. Scaling this to interstellar levels would require leaps, but so does everything about Starshot. The bonus: such infrastructure could revolutionize Earth's energy grid long before the first probe launches, making clean power abundant and cheap. The ecological calculus gets nuanced when weighing short-term costs against long-term payoffs. Constructing the laser array would demand mining rare earth elements, manufacturing carbon-intensive materials like graphene, and potentially disrupting local ecosystems with construction. Yet analogous megaprojects, the Large Hadron Collider, Panama Canal, or Three Gorges Dam, show that environmental trade-offs often accompany transformative leaps. The difference here is opportunity. Starshot's energy systems might pivot civilization toward sustainable abundance if designed holistically. those same lasers, after propelling probes, could zap space debris or power lunar bases, amortizing their footprint across multiple frontiers. Critics argue no justification outweighs ecological harm, but history suggests exploration's indirect benefits often redeem its sins. The space race birthed solar panels and water recyclers. Starshot's renewable push could leave legacy technologies that outshine its primary mission. Perhaps the ultimate environmental win lies in perspective. Nothing motivates planetary stewardship like seeing Earth as a fragile oasis against the cosmic dark. Those first Alpha Centauri images won't just show alien worlds. They'll reflect back our own, a marble worth preserving not just for us, but for whatever or whoever might one day find our microscopic messengers in the void. The eerie silence of the cosmos has haunted scientists for decades, a mystery so profound it's named after the physicist who first voiced it aloud. The Fermi paradox asks a deceptively simple question: if the universe is teeming with life, where is everyone? Statistically, with billions of habitable planets in our galaxy alone, Earth should have been visited, colonized, or at least pinged by now. Yet our radio telescopes hear only static, and our skies remain stubbornly empty of interstellar tourists. Could Project Starshot's very existence hold a clue to this cosmic riddle? Consider the possibility that advanced civilizations face the same hurdles we do. Starshot's approach, tiny probes propelled by lasers, might not just be humanity's best bet for interstellar travel, but everyone's. Think about it, sending massive, crewed ships across light years requires mind-boggling resources and time. But a fleet of microscopic probes, they're energy-efficient, scalable, and far less risky than biological travelers. If other civilizations converged on similar logic, the galaxy might be swimming with invisible, AI-piloted scouts too small for us to detect. They'd zip past unnoticed, like a mosquito whizzing through a football stadium at night. There's a darker interpretation, too. Starshot's reliance on laser propulsion reveals a brutal truth. Relativistic speeds make two-way communication practically impossible. A probe reaching Alpha Centauri would take over 4 years just to say, "We arrived," and another 4 for its message to return. For civilizations separated by thousands of light years, dialogue becomes meaningless. You'd need patience spanning millennia. This communication lag might impose a universal rule. Once societies go interstellar, they go silent, not by choice but by physics. Then there's the chilling zoo hypothesis. Starshot's nanocrafts are designed to observe without interfering. No landing, no contamination, just passive data collection. What if that's the galactic norm? Advanced civilizations might have strict protocols against meddling with developing worlds, leaving us untouched like a nature preserve. Our own probes could one day follow this ethic, studying alien biospheres from a discrete distance. The paradox isn't that no one's out there, it's that everyone's playing by rules we don't yet understand. But perhaps the most humbling answer lies in time. Starshot aims for a 20-year flight to Alpha Centauri, but that's a blink on cosmic scales. Intelligent species might rise and fall in the span it takes a probe to cross between stars. Imagine a civilization launching its own Starshot-like mission 1 million years ago, only to go extinct before their creations arrived. The galaxy could be littered with orphan probes, their senders long gone, their data echoing into oblivion. The paradox's resolution might not require aliens at all, just introspection. Starshot forces us to confront how we'd appear to others, a species on the cusp of interstellar capability, yet still confined to our cradle. If we're this close to reaching out, why couldn't others be too? The silence isn't proof of absence. It's a mirror reflecting our own infancy, and a challenge to keep whispering into the dark until someone whispers back. The nanocrafts of today could be the interstellar cargo ships of tomorrow, if Starshot's vision scales as radically as its founders hope. Right now, we're talking about probes smaller than a fingernail, but imagine doubling or tripling their dimensions while maintaining the same featherweight design. A slightly larger sail could capture more laser photons, boosting speeds beyond 20% light speed. Engineers speculate about exotic materials like atomically thin diamond films or self-assembling metamaterials that could create sails meters wide yet weighing mere grams. These wouldn't just be upgrades, they'd be game changers, cutting the travel time to Alpha Centauri from 20 years down to 15 or even 10. Suddenly, missions to farther stars like Sirius or Tau Ceti enter the realm of possibility within a human lifetime. Swarm intelligence takes this a step further. Instead of single probes, picture hundreds launched in coordinated waves, a constellation of scouts fanning out across alien star systems. Some could specialize in planetary surveys, others in asteroid belt mapping, while a third group acts as communication relays. AI would orchestrate this ballet autonomously, sharing data between probes to maximize scientific return. Japan's successful Slim moon landing demonstrated how networked spacecraft can recover from individual failures. Applied to Starshot, this redundancy could make the mission virtually failure-proof. Lose half the swarm to cosmic hazards, the remaining probes adapt their objectives on the fly. Materials science lurks behind every potential leap. Current sail prototypes rely on ultra-thin sheets of reflective aluminum, but labs are already testing quantum dot coatings that convert incoming laser light into additional thrust. Other experiments focus on photonic crystals, nanostructures that manipulate light with extreme efficiency, potentially reflecting 99.99% of the laser's energy instead of today's 99.9%. That tiny difference adds up to massive performance gains over light years. Then there's graphene's potential. A single atom-thick layer could theoretically withstand the laser's fury while weighing almost nothing, though production at that scale remains a challenge. The propulsion system itself could evolve beyond recognition. Future versions might employ space-based laser arrays orbiting megastructures free from atmospheric distortion, powered by vast solar farms in permanent sunlight. These could sustain acceleration far longer than ground-based systems, pushing sails to 30 or even 40% light speed. Some theorists even toy with antimatter-assisted launches, where tiny antimatter bursts give probes an initial kick before lasers take over. It sounds like overkill until you realize that shaving 5 years off the journey might mean the difference between scientists seeing results before retirement or leaving discoveries for the next generation. Perhaps the most transformative upgrade won't involve hardware at all. Machine learning algorithms currently train on simulated space data, but imagine feeding them real-time telemetry from a dozen interstellar missions. Each probe that returns data or fails spectacularly would make the next generation exponentially smarter. Future AI might predict micrometeoroid swarms with eerie accuracy or invent entirely new navigation strategies we can't yet conceive. This isn't just iterative improvement, it's evolution at warp speed, with each mission cycle compressing decades of trial and error into months. The ultimate scalability test lies in cost efficiency. Current estimates peg a single Starshot launch at millions per probe, but mass production could follow the trajectory of microchips where prices plummet as techniques refine. Silicon Valley's fabrication plants already print circuits by the billions. Adapting those methods to spacecraft manufacturing could drop unit costs to thousands or even hundreds of dollars. At that point, sending probes to every nearby star becomes economically feasible, not as a once-in-a-generation event, but as routine scientific exploration. What makes these possibilities so electrifying isn't just the technology, it's the paradigm shift. For centuries, space exploration meant building bigger rockets to carry heavier payloads. Starshot flips that logic, proving that minimizing and multiplying might be the key to the cosmos. The project's true legacy may not be the first probes we send, but the realization that our interstellar future isn't about building one perfect ship, it's about launching an army of imperfect ones, each generation bolder and brighter than the last. Stories from the front lines of science often start with a spark, a moment when the impossible suddenly feels within reach. For 14-year-old Maya from Toronto, that spark came in 2021 when she watched a documentary on Project Starshot. The idea that humanity could touch another star in her lifetime transformed her vague interest in astronomy into an obsession. She spent the next summer building a miniature light sail in her garage, calibrating it with laser pointers borrowed from her school's physics lab. Today, she's interning at a university aerospace program, her notebooks filled with sketches of interstellar probe designs. Maya's story isn't unique. It's part of a wave of young minds who see Starshot not as science fiction, but as a career path waiting to be charted. What makes this project so electrifying for the next generation isn't just the technology, it's the timeline. Unlike century-long visions like Dyson spheres or generation ships, Starshot operates on a scale that today's teenagers could witness. High school freshmen might analyze data from Alpha Centauri before they turn 40. That immediacy changes everything. Suddenly, equations in textbooks aren't abstract exercises. They're the blueprints for humanity's first interstellar postcards. Teachers report students staying after class to debate laser diffraction or sail materials, while science fairs overflow with projects testing radiation shielding or microthrusters. The message is clear: space isn't just for astronauts anymore. The engineers who'll perfect Starshot systems might currently be coding video games in their bedrooms or tinkering with 3D printers in makerspaces. The project's openness amplifies this effect. Breakthrough Initiative's online portals offer free access to technical papers and challenge students to solve real mission problems. Last year, a team from Mumbai proposed using quantum dots to enhance sail reflectivity, an idea now being tested in lab simulations. Another group in Berlin developed an AI model predicting micrometeoroid densities along potential flight paths. These contributions aren't just academic exercises. They're proof that the barriers to interstellar exploration aren't just crumbling for scientists, they're disappearing for anyone with curiosity and grit. Yet inspiration alone isn't enough. Starshot's legacy hinges on transforming wonder into workforce. Universities are scrambling to adapt, introducing courses blending astrophysics, nanotechnology, and AI disciplines once siloed now fusing under interstellar demands. Scholarships targeting underrepresented groups in aerospace are prioritizing applicants who articulate how diversity drives innovation. Because solving problems no one's ever faced requires perspectives no one's ever tried. Even children's media has caught on. Popular animated shows now feature characters designing light sails instead of magic wands, normalizing the idea that shaping humanity's future among the stars isn't extraordinary, it's expected. The deeper lesson here transcends spaceflight. Starshot embodies a mindset shift that impossible is just a temporary label awaiting the right minds to peel it off. When 17-year-old Javier from Mexico City submitted a proposal for swarm-based interstellar communication relays, he wasn't discouraged by his lack of credentials. He was inspired by the project's co-founder, Stephen Hawking, who famously said, "However difficult life may seem, there is always something you can do and succeed at." That's the real gift Starshot gives: permission to dream without limits. Because the kids sketching Starship designs today aren't just imagining the future, they're already building it, one equation, one prototype, one laser beam at a time. And whether their contributions eventually help reach Alpha Centauri or simply inspire the person who does, that's how revolutions begin, not with a single leap, but with countless small steps forward, each one stretching the boundary of what we dare to believe is possible. Project Starshot stands as one of humanity's most audacious bets, a wager that we can outsmart the vastness of space, not with brute force, but with brilliance. This isn't about building faster rockets, it's about reimagining the very concept of travel, shrinking spacecraft to the size of a postage stamp and riding beams of light to another star. The vision is staggering, a fleet of nanocrafts propelled by lasers cutting the journey to Alpha Centauri from millennia to mere decades. But let's be clear, this is no smooth ride into the cosmos. The challenges are as immense as the ambition. We're talking about mastering laser precision over millions of miles, creating materials thin yet strong enough to survive interstellar chaos, and designing AI smart enough to navigate the unknown without human guidance. Each hurdle is a mountain, and Starshot aims to climb them all in a single generation. What makes this endeavor extraordinary isn't just the science, it's the shift in mindset. For centuries, interstellar travel was the stuff of dreams, relegated to distant futures or fictional worlds. Starshot drags it into the present, transforming someday into within our lifetime. It's a reminder that the greatest leaps begin not with resources, but with resolve. Think of the Wright brothers' first flight, a wobbly 12-second hop that rewrote history. Their triumph wasn't in the distance covered, but in proving flight was possible at all. Starshot embodies that same spirit, challenging us to ask not, can we? But how soon? Yet the project's true legacy may lie beyond technology. It's a mirror held up to humanity, reflecting our deepest traits: curiosity, resilience, and the unshakable urge to explore. Every equation solved, every prototype tested, is a vote of confidence in our collective future. That's why this isn't just a mission for scientists or billionaires, it's an invitation to all of us. Whether you're a student sketching sail designs, a programmer optimizing navigation code, or simply someone who gazes at the night sky and wonders, you're part of this story. The stars aren't just for dreaming, they're for reaching. So here's the question: what role will you play in this journey? Drop your thoughts in the comments. Are you team optimist, betting on a launch within our lifetime, or team realist, convinced the hurdles are still too steep? And if you're hungry for more mind-bending futures, hit subscribe. The next chapter of human ingenuity is being written right now, and you won't want to miss it.